Right, so it's 9:04 in Central European time. I think this is a good time to start our webinar today. So there's 17 attendees so far, but hopefully more will join throughout the course of the talk. So good morning, everyone, or good afternoon, good evening, depending on whereabout in the world you are located. So welcome to a new episode in the Materials Square monthly series of webinars on scientific computing topics and applications. So my name is Gabriele Mogni, and I am the European representative of Materials Square based in Belgium. As you may know already, Materials Square is an innovative cloud-based software as a service platform for performing material science atomicity simulations, which is developed by Virtual Lab, a startup company based in South Korea. We believe, in fact, that our solution for performing modeling of materials and chemicals applications directly on the cloud could be of great benefit to the R&D efforts of your organization. And we therefore invite you to please explore our simulation services and products on our website, which is www.matsq.com. So matsq.com. Okay, so for today's webinar event, it is our pleasure to have Professor Frederik Tillens from the VUB University in Brussels, Belgium, as our guest speaker. So Professor Tillens is today at the head of a group of materials modeling and computational chemistry at VUB University, and he's also associate professor at Sorbonne University in Paris, France. So the title of his talk today is Computational Chemistry as a Missing Piece in the Characterization Puzzle of Biological Mineralization. And in his talk, he will tell us about how solids of biological origin, such as hydroxyapatite or calcium oxalates, are directly involved in the so-called chemistry of life, in order to understand, therefore, the origins of life on Earth. So for this purpose, his research group has performed a series of DFT studies on different interfaces involving such materials and investigated them by calculating the spectroscopic properties, which were then compared to experimental data. Also, at the end of the talk, we'll have some time for question and answers. For that, I invite you to please enter your questions in the Q&A section at the bottom of the screen. Okay, so Professor Tillens, welcome to our webinar event, and thank you again for your availability to participate. So the floor is now yours, and you are now ready to present, I believe.
Thank you very much. Thank you very much, Gabriele, for giving me this opportunity to share my results, my research topic here with you in this seminar. I have not much experience of the type of people that are attending, so I hope you will enjoy, or you will at least take up some interesting messages. So as was mentioned before, there is then a Q&A session that I would love to attend, even live after the live, I mean, well, here online then, live after the talk. So there were, it was asked to me that I would present a presentation or an overview on the topic I liked in about 40-45 minutes. I tried to respect this time, so we will go on. So indeed, the title is about, in fact, the calculation, the modeling of biological minerals. Yes, and the idea is to compare that with experiments, and so that be joining both forces, experimental and theoretical modeling simulation forces, in order to have a complete picture on what is going on in this family of materials. This family of materials is quite interesting because it is on the interface, yes, I can use this word, although you will listen, or you will hear this word many times here in this talk. It is on the interface of different disciplines. Yes, you see, well, I will present something on modeling, maybe mainly based on physical chemistry, but I talk about something which is biological and which is at the same time inorganic. So we have many different fields that you are tackling. So let's go to the introduction, if I can, go on. So everyone sees the screen, and Yeah, we are now on the second slide. Can everybody see it? Yes, I suppose.
Yes, we can
Okay.
see your slides very well.
Okay,
Thanks.
thank you very much. So the introduction, I've selected two families of materials because I can, yeah, otherwise I would talk the whole afternoon or all morning. And but it's mainly the idea to show you some examples of what we are doing. Yes, it's punctual examples. And the first example that I would like to show is about kidney stones. Kidney stones, it's a pathological calcification, globally, global concern. You have this everywhere in the world. And we know that these calcifications, they are mainly made of oxalates. And most of the kidney stones are made of oxalates. There are other types of kidney stones. They contain other minerals, like what you see here, cysteine, for example, and cysteine. But we have other amino acids, can it be, but other bioorganic molecules that can crystallize or just precipitate in and around the kidney environment. So the question is, yeah, how can we model that? As you see, it is quite complex because we are in a biological environment. We are not working in perfect water, very pure water, water solution. So here we have to make only models, let's say approximations, in order to obtain any results that can be discussed in this framework. Then a second, sorry, just a second, just a second. Wait, just a second, please. Yes, sorry. Sorry, excuse me. It was my team was on, and we are on bone. The second is bone, and this is also a biological mineralization where we have hydroxyapatite as a main compound of it. But the main problem here is the description of the structure. Yes, we have a system that is in interaction with a physiological environment, and we have also then the presence of a lot of defects. Then the way how these defects are distributed over this hydroxyapatite, which is the main compound of bone, will determine the properties of the structure. So in general, if you want to have more information on what kind of materials we study, you can go to our new website here that I just pasted the link. We study also other types of materials going to inorganic or catalysis and metal structures, metal nanoparticles, and so on. So let's go on to the topic of today. So the pathological biological mineralization of oxalates, in second part, bone. So on the oxalates, we have three possible, let's say, environments that are studied, and that can be used for understanding how these crystals grow, yeah, how these crystals evolve. And from this information, it's interesting to know what, well, yeah, if we talk about medical and pharmaceutical applications, it's interesting to know from the properties, the physical chemical properties, how they were made of, yes, how they were made, how they grow. So first thing is that these oxalate, calcium oxalate crystals, they are made of, they consist of platelets, let's you see here, that are of these hexagonal shapes. And this is what you find when you take samples out of kidney stones. Now, in fact, calcium oxalate does also exist in the nature, in quarries, so as a mineral, and this has another crystal shape, crystal morphology, as you can see. Now, in synthesis, we were able to do, we were able to synthesize both type of morphologies. Yes. Now the question is, how can we explain this change in morphologies depending on the environment? So very easy. How do we model? Well, the idea is to use as many as we can the DFT, yes, density fractional theory. So we start with a unit cell, which is represented here with the three types of systems that we have in our unit cell. So the oxalate anion, the calcium cation, and the water molecule. And we have in order to obtain the morphologies, we will see that we need to have some interfaces. We need to have some surfaces exposed. Okay. So after having these structures, the bulk structure determined using the data from experimental results, and then refined and optimized using density fractional theory, we can go and split up this bulk into two parts where we introduce a vacuum in the middle, and so we see appearing the surfaces. Yes, we can do this in different orientations. This is another course. I will not go into details. And then the problem is, now we have probably water everywhere there. Yeah, so we need to introduce a water section in this unit cell. The question is, water is quite difficult to model because we have an amorphous phase. Water is amorphous, especially at the temperature where we want to work. Since here we work in biological in biological environment. So this is not 0 Kelvin. Yes, so we need to have a water structure that is reasonable and in agreement with what we have in real life. So now then we can use some molecular dynamics and equilibrate the water structure in interaction with the surface. This is, let's say, a very important part of the studies in general, which is the study of the interface of water with the surfaces in plural. So in order to make the calculation a little bit more rapidly, we found out that we can go to just a solvation layer or two in order to speed up the calculations. And with these calculations, with these models, we can calculate surface energies. As we will see, surface energies is what is needed in order to predict the morphologies. So this is how we calculate the surface energies. We calculate them by using the difference, in fact, between the bulk and the surface model, which is mainly the energy you need to cut a surface, a bulk, to cut out a surface out of the bulk along a certain orientation. And this per surface area unit, yes? This can be 2 in some calculations. and some studies you see that there is a 2, because in fact, as you see, when we cut a unit cell in a periodic environment, then of course you have below and above the slab that you create. When we add water, then in fact what happens is that you add to this formula the interaction of the water molecules. Okay, so it's the same, but also per surface unit. But we are introducing the the energy of the water. Now, in order to obtain these morphologies, there is a thermodynamic law that helps us to draw these model morphologies. And this is the theorem of Gibbs-Wolff that will help us with that. And it has the following form. So we have a delta G, so the free energy of Gibbs, which is equal to the sum over the free energies of one orientation multiplied by its surface. This means that in fact, for free energy, constant free energy value, we have in fact an opposite relationship between the surface area and the surface energy. Yeah. Low surface energy will expose large areas. Now we introduce also a parameter here that helps us, in fact, to fit a little bit the results, because as we will see, crystal structures are not only determined by thermodynamics, but also by kinetics. And in order to have an idea on how important is the kinetics in the structure, we can introduce this relationship where we, in fact, multiply our surface energy with a parameter lambda and introduce this. And so we can then, in fact, evaluate how important is the kinetic part in our system, in our morphology. So let's first go to the first example. You see there, I have not explained this yet, but we have here a COM, you see this COM, which is in fact a polymorph of the calcium oxalates. I forgot to tell you that we have many, mainly 3 polymorphs of calcium oxalate. You have the monohydrate, the dihydrate, and the trihydrate. And in kidney stones, we have mainly the mono and the dihydrate species. Okay, here we will show both of them because both of them are present in kidney stones, and we can see them with the electron microscope or with other microscopy, and we can compare our proposed morphologies with the experiment. So let's first start with the simple monohydrated case, and let's say that we do the same. We calculate the surface energies here along all these different orientations that we've chosen. Yes, these are the different orientations. See this is the x-axis. Yes, so we do this with DFT. Yeah, so PBE functional D3 correction. I don't know. If you have some questions, you can always ask me in the chat. And then we have here, we plot here our surface energy calculated with the formula that I've shown you. So here are the dots and the corresponding to these values on the several surfaces. We take out the most important ones, yes, and this is what we obtain when we are calculating without water. Without water, this is like growing crystals in space, yes. So this is not quite realistic. So then let's introduce the effect of water. Now, if we have the effect of water, we obtain the following graph, which is shown here with the orange, dots, big dots, and then we see that in fact the trend is changed. And if we use these surface energies with the formula of Gibbs-Wolff, then we obtain this morphology. The problem is, if you remember what we have seen before, that is that the morphologies were hexagonal platelets in kidney stones, and then something a little bit more three-dimensional in the quarries in nature as a mineral. Okay, so we still don't have it. So what is the problem? Well, here is the thing that comes up now, is that in fact this is purely thermodynamics, so it doesn't take into account any kinetic effects. So we don't have any barrier here to go from one phase to another. And this is what we have to introduce, let's say, with a kind of approximation. And so let's now imagine, so what happens if you delete, for example, one surface, one orientation, and you take it out of the equation, and then you will see that there will be directly a difference in the morphology. So if we take away the 0, 0, 1 morphology, then we will see that the morphology becomes more platelet-like. And this is what we want. But what does it mean? That means that in fact our surface energy here, is in fact too big, too high. So we have to destabilize this thing. Yeah. So this point, in order to be sure that it is not interfering with the other surfaces. And this means that this system is probably inhibited kinetically. Yeah. But we are still not happy, as you see, because what we want is this type of crystals, yes, hexagonal. So there is something else. We need to grow this surface 0, 1, 0. And how do we do that? Well, in fact, it is by lowering, making more stable our 0, 1, 0 surface. And this is something that we see. So if we do that, we obtain the structure which is reasonable. And we see that, in fact, with the growth of the crystals, we see that, in fact, with the time, we see that there is some competition going on. And we start with a very stable one, and it becomes, so the kinetics comes again, and we see that the other surfaces will start to influence it. And then we see a change in morphology with the time. Okay, so this is the site here. This site, this orientation that moves, that changes the function of the time due to the kinetic effects. Okay, now we can go further on. So if we make this kind of correction, then we obtain the crystal structure that we see in nature. Yes. So there is a difference between the biological one and the mineral one. Good. Now we can do the same on the calcium oxalate, but the dihydrate. And these are the start structures. So we have in kidney stones, we have this octahedral structure, so double pyramid, and we have also the same structure, but with this kind of this part that is inside between the two pyramids. So this is in kidney stones. In synthesis, we can't introduce this, but we have seen that by adding additives, typically complexing agents, there are many of them, we see that we grow here a surface in the here in this area, showing that we have here, as you see, we show here a 010 surface appearing. Yes, so you see here this enlarged octahedral structure. So let's try to do the same thing. I can go faster here because I don't know how much time. In fact, I still have. I lost the time, but it's the same procedure. So without water, we have this. It doesn't seem to be close to what we want, although it is closer than for this comb structure. As you see, we see the pyramids already. Yes, you see them, but there are more surfaces here present. In water, we can even delete, avoid one surface, but still there is this surface that we don't see at all experimentally. So this is something that is also inhibited experimentally. So we need, in fact, to correct it to obtain this structure. Yes, that is in agreement with the experiment. Now we can make an overview, and then we can see, in fact, what is the effect of each orientation and the effect of water on the morphology. Okay, with and without this correction. So now I talked already about the effect of additives. So now there's something that I would like to show you, which is quite interesting in technically in the modeling, but also in applications in therapeutic applications, pharmaceutical applications. This is that there are some molecules that can attack, dissolve, or if you talk about inorganic chemistry, can corrode structures, crystals. So, there has been seen that some molecules in green tea, I go directly in green tea, that attack these calcium oxalate kidney stones. Now, how did they see that? Well, this is an Asian study I think in China, where they compared the kidney stones of the green tea drinkers with others, and there they saw that the kidney stones of the green tea drinkers are, let's say, much more destroyed, if you can say it like that. Okay, and here is a picture. So we can see that. I see you see my cursor. You see these pyramids that you've seen for the cod structure, the dehydrated, the calcium oxalate dehydrate structure. You see that there are some craters. You see here it's like a start of dissolution, of corrosion. This means that there is an additive that makes a complex with the surface and is so strongly absorbed that it takes out an ion, a calcium ion in particular, and we will try to have a molecular view on that in the next slides. In general, what we can say is that this green tea, this molecule, it's the if you read the whole name is epigallocatechin gallate. I will call it catechin for the easy. For not making it too difficult. And so what we see is that, in fact, it orients crystallization. So we have, of course, this 010 that appears, and we have a corrosion that appears, especially on the 101 surface, okay? And this is what we would like to model. So how do we do this? We use molecular dynamics for that, yeah? So you remember, this is what we did. Oh, yeah, this is for the COM. Okay, sorry. This is for the COM. For the COM, we can have some similar systems. So, but here it's especially the technique that I would like to show you. Yes. So we have our oxalate surfaces. Yes, and we have our adsorb, our complexing agent. So the idea is to study the interaction of this molecule, our catechin molecule, with the surface. Yeah. So first we need to define some variables in order to follow what's going on. So in order to study the adsorption, we need to have a first logical parameter, which is the distance between the molecule and the surface. The second one is what we call the coordination number. Coordination number, yes, defined by here. I don't go into details, but in fact, it counts the number of neighbors. Especially when you're close to the surface, you will have a high number, a high coordination number. Yes. So in order to have a good surface, a good adsorption, a strong adsorption, this will be translated by a low D and a high Cn. Yeah? A short distance and a high coordination. This is what we will follow. Yes. So now we can go, in fact, to a molecular dynamic simulation. I can show you this during the next 30 minutes, but this would not be very interesting because this is standard molecular dynamics, and this is deterministic. So we have to wait until the molecule goes through the water, through the water and adsorbs on the surface. You don't see here anything; it looks white, but in fact, you cannot see the water molecules that are present in order to visualize better the system, right? So what we see is that it's there. It's maybe approaching, but it's very slow. So it's not very interesting to study, and we don't have the time to wait. So we need to find new methods. We need to find new strategies in order to obtain these geometries of the adsorbing complex. Just some technical details here. We have this. We've done this with Gromos force field, the canonical ensemble NVT 1 nanosecond, and you see we work at the 37 degrees centigrade. So we go further on, and we have to go to an. Oh, sorry, I went too fast. I see. Yes, this is the point. Yeah. Maybe I will stop this before because other. Yeah, good. So now what we do in order to accelerate the search of our adsorption site, we used this a special method, which is a special method or strategy linked to the sorry to interrupt, but I've already a question here. I saw that. Maybe I can answer it directly. So why choosing a temperature of 0 K that we can reach experimentally? But the question is why choose that we cannot reach experimentally? Is that what you say? Probably, yeah. Well, in the morphologies, we only look here thermodynamics. You're right. At high temperature, it will be different, and we will then include kinetic, the kinetics of the system. But you know, we don't have the calculation power in order to do kinetic structure simulations on every orientation. Because if you want to model a morphology, we need to have at least 3 or 4 orientations, and yeah, this is a lot of work if we want to I mean, I think it's not possible. So we only use thermodynamic data, and we correct them with the kinetic parameter. Yes, did I answer the question? Okay, so we continue. So in order to accelerate the process, we introduce a replica molecular dynamics, which means that in fact we use different starting geometries, and we start to do our a combination of all these molecular dynamics. And once we found a better structure, we use that to modify the one which was better before. So in order to make a selection of the best structures, in order to not go through all the other situations in our molecular dynamics. Maybe you can see this on the video here that we have here. Is that in fact on the scheme we started 4, but in fact we started with much more. The syrup equals 46, but we jump from one molecular dynamic simulation to another every time we found a better structure than the one before. And so we refine until we have a better structure. And the better structure is when we have an interaction, because we lower the energy considerably. So here again, we use force fields in order to do it faster. We don't use the dynamics here, the DFT, the molecular dynamics. It's again canonical, 1 nanosecond, and we have here 46 replicas. We have to introduce also some differences in temperature, because we need to cross some barriers. So in order to obtain a geometry, we have to do this technique. You see the molecule is jumping, and this means every time when he finds a more stable geometry, you see, it jumps there and then it's there. It will be more and more present at the surface. So in fact, you accelerate your search for an adsorption geometry. Yes. Okay, there's a second question. Can we use XRD pattern to predict morphology? This is a good question. I don't morphology. Yeah, it is typically something you see with a microscope. With XRD, is typically you could see the structure, the bulk structure, also the size of the crystallites. You can do that also, but this is pretty much it. Depending of course how big it is. Yes, maybe if your surface in a monocrystal, maybe if you expose one specific surface, then maybe you can see something, but I have some doubts. But I would say XRD is not here the good way. It is typically a bulky system, a method to study bulk structures. Okay, then, so this is then our way to find this adsorption geometry of adsorption, yeah? Adsorption of the catechine molecule on the of the catechine molecule on the surface. And so we can extract our molecule, our geometries, and we can analyze then with DFT, sorry, the adsorption of these molecules at the surface. Okay, which explains us then also the mechanism of adsorption, and maybe also to propose a mechanism of this corrosion, if you remember. So the complexation of a calcium ion, so these green balls here, with the molecule. Yeah. So the final aim of the study would be to propose a mechanism of this corrosion process. Yes, and this is what we wanted to do. With molecular dynamics, and we did this for the different surfaces that you see here. So we have here we have the catechine adsorption on the 1, 0, 0 surface, 0, 1, 0, and the 1, 2, minus 1, and we see that there is some favorable adsorption surfaces or orientations and unfavorable. Okay, and this is what has been calculated. How did we do that? We do that with metadynamics. And we use the parameters as our variables to follow that we have defined before, the distance here on the x-axis and the coordination number. Yeah. So in order to have adsorption, we have to be in this area, small distance, high coordination number. And if you are solvated, in fact, then you are far away from the surface, okay, and you have a low coordination number. Yeah. So you go from solvated to adsorbed. Okay, and then we can in fact calculate on every point our free energy, which is in fact a part of the potential energy surface. Yes, this is a partial potential energy surface. Yeah, this gives us an idea on how this mechanism of adsorption occurs. Okay. So here we have it for COD. I don't show everything, but these are some examples. Yeah. So here we have it for the other surface, and you go from here to there, and we can so predict our adsorption energies. Yes, and we can stick some values on it. Yeah, that's what we have seen on the picture before. And finally, I would like to show you the adsorbed situation. The problem, there is a problem here, as you will see. So here it is quite sticked. Yes, it's stuck. I mean, it's on the surface. We have a very favorable adsorption geometry where complexation with cations is going on. The problem is that due to computational time limits, we did first the calculation with the frozen surface. Yes, so maybe the system will change if we have the upper layer of our crystal also be included in our molecular dynamics, DFT molecular dynamics simulation. So here we can then see if there is really an extraction of this calcium cation out of the crystal. Okay, good. I think I came in the second, we can start on the second part of the talk. I don't know what is the time, just to 38. Okay. How much time do I have for this part, so that I can maybe keep into the time schedule? I see it's almost 40. I think we started at 10, so I have 10 minutes or something, or 15 minutes. Is it okay?
I would say, yeah, 10 minutes, about 10 minutes.
10 minutes. Okay, then I will go fast. I will first introduce a little bit what is bone. Very short. A bone is yeah, a mineral which is composed of calcium and phosphate, yes, and water. But many other elements. You have carbonates, you have chlorides, you have well, protons all over the crystal. You have all other biological complexing agents, again, as we've seen for the kidney stones. The problem with the bone is that it is an hierarchical structure. So what you see macroscopically is not what is present nanoscopic, at the atomic molecular scale. And this is what we want to propose. There's still a lot of debate. So how does bone looks like at the atomic scale? And what we see here is, in fact, we have some platelets of calcium phosphate. It crystallizes under the form of a hydroxyapatite, yes? And in between, we have, in fact, a kind of ending where there are some proteins, collagen, maybe you know that, and they will help you to destabilize your bone and also make it stronger. The mixture of this protein, collagen, and the calcium phosphate particles makes bone material to have its particular properties. Yes. So now the question is, how can we model that? How does it look like? And typically what we will model is, if you see these platelets here, they come in contact in this interface here with the proteins. So the question is, what is the interface here? Okay? And this is typically a surface of hydroxyapatite, like structure, I would say, not completely. And they are separated with each other, the platelets, I mean, with a distance which is very small. Let's say a couple of 5 angstroms, something like that, 10 angstroms. It is very, very, very small. In this nanometer, between everything happens. There is a flux of ions and so on. And so, in order to model that, experimentalist people have tried to synthesize this kind of material. Let's say it's not really synthetic bone, but it is a bone-like structure which is made of layers that is made that corresponds to the distance that we have in real bone. So we have a kind of very nice homogeneous structure in layers, and this will help us to compare with our theoretical calculations. Yes. So this is how it looks like at the interface. We have, in fact, a kind of crystalline structure. Then we have a kind of undetermined amorphous-like structure, which might be crystalline structure, which is going out of the symmetry group. There was a question before, can we use XRD? Well, yeah, XRD is something very rigid. Once you are out of a space group, then the crystallographs, they are a little bit puzzled, and then they have to say, yeah, we lower symmetry, or we have an amorphous structure. And this is the question, because this is this part with the interface of water, which is in dynamical equilibrium. We are, in fact, here an undetermined phase. Yes. Okay, there is another question in the meantime. Does NVT ensemble give unrealistic pressure or unrealistic artifacts? Yeah, to be honest, I cannot answer to that question. I know that there are some corrections being done, but if you want to know more about that, then maybe I invite you to send me an email on that. Yes, because this is really technical. And we have some procedures for that to correct that. Yes. Good. So we go to the structures itself. Here are the different models we can make. I would like to go faster to that. So, in fact, the different interfaces. You see that's crystalline, amorphous, crystalline with the solution and so on. Yeah. What is important here is, if we want to make a model of the bone, And for that, we are always going back to experiments. And we see that, for example, if we do a 2D NMR here diagram, we have proton, phosphor, and we see two species here, yes, of phosphor. Yeah, and this means that we have a phosphate and an hydrogen phosphate group. Yeah, so in our hydroxyapatite or our calcium phosphate system, we should have both type of phosphates. And then there is a question. I go very fast. It's because in hydroxyapatite, we only have this type of phosphates, pure for PO4. Yeah, we don't have the HPO4, but there is a polymorph in nature that exists, and this is octa-calcium phosphate. And there you have, in fact, a structure which contains some structure like part that is looking like apatic, so hydroxyapatite. Yeah, and we have a zone where we have the hydrogen phosphate. So this can be an ideal model, an ideal model start structure for our simulations. And this is what we have done. So we made a model, we make our surfaces, we introduce water, we equilibrate with the surface, and we start to see what happens. Again, we can compare it with our systems that we made. Remember, these are synthetic calcium phosphate structures with these layered structures, yes, with these nanometers in between. And we did it the same. So we tried to find out the structure, the effect of amorphization, yes, with at the interface with water. Maybe, yeah, sorry. Yeah, you see, so we have the water interface, and we can see here in this part how the structure evolves. Yeah, so this is the water interface study. We can study this with many different things. I can go further on. I don't know how much time I have. I have the impression I have to hurry up. We can do some typical molecular dynamics analysis with the G of R analysis. And we can also do, and this is what I would like to show you before finishing, we can also calculate some derived properties. Because what is important is once we have a model, we want to check this with our experiments, and spectroscopy is the ideal tool for that. Let's see. Good. Okay. And yeah. So okay, we see here the mobility of water. We saw an interaction and an exchange of water molecules from the bulk to the water bulk, and vice versa on the hydration layer. We can also add some extra water molecules in order to see what is the effect on the density of the water in between, because we are working in confined environment. 1 nanometer or 1.2 nanometer that you see here is very small. So we can probably think on some special properties that are emerging out of this model. Typically what we see in other systems is that we have some automatic reorganization. We call that ice-like structures, but it's at room temperature. Yeah? So we wanted to have a kind of water-like structure because this is what we think is important in the chemistry of life. Yeah. The dynamics, I don't think skip that. So what I want to tell here more is that in fact we can make this model much more realistic, and for that we need to add, you see here, all the other ions in the interface in the interface part. You see, so this is all the things that we can do. We can make this kind of physiological soup, and then see what is the interaction between the different ions, and how the surface interacts, how it behaves in the presence of these ions. Okay, so now this is something I would like to emphasize. Especially there was some question now then on XRD. Well, XRD is very important for us, but why? Because in these biological structures, most of the structures are in interaction with biological molecules, and we have not very precise or very nicely defined crystal structures. There is a lot of amorphous structures there, yeah? And XRD can help us to determine the amorphous structure. How do they do that? Well, with crystal with the X-ray diffraction technique, or other, you can do the electrons, neutron, we can obtain pair distribution functions. What is this? This is the distance between two atoms. Yes, and we can, for example, here you see PO. So this is the distance of PO. Yeah, P phosphor oxygen, and we see how many times this occurs. Okay, so this is, and we see this for different, we see different peaks arising, which correspond to different couples, pairs of atom-atom distances. And this profile is a fingerprint of the amorphous structure. So now, if we have this, yes, we can in fact use this to fit an amorphous structure that we have built, yes, to the experimental one. So this is very powerful. We can do this with a reverse iterative technique. We did this with the reverse Monte Carlo, for example. So we know what we want to have as a result for distances, and we try to calculate the structures with Monte Carlo. Yeah. So in order we fit the amorphous structures, the positions of the atoms, to the graph here, to this diagram. So the PDF. Okay, and this is very important in all these family, in all the families of materials that we study, this biological mineralization. I don't know how much time I have left. Can I have some 5 minutes more, or do I have to come to the conclusions?
No, it's fine. I think you can spend another 5 minutes. Yeah.
Okay. Thank you very much. So this is the last part that I would like to show, and this is, in fact, an application also on the use of molecular dynamics, is that we have an interface here. Yes, this is our hydroxyapatite, I have the water, and we've put a complexing agent here, citrate or citrate. Yes, and the question is, can we obtain from our molecular dynamics and spectroscopic fingerprint or spectroscopic spectra, an infrared spectrum, for example? This is very important because we have done a direct comparison, a direct possibility to compare with the experiment. Yes, and we have a spectrum on which we can put or stick a molecular model to it. So this is very powerful. You have a spectrum, and then you say, "Ah, look, the atoms are like that. They are positioned like that." And this is what we would like to do. So the molecular representation of an infrared spectrum, and so. We did that for the hydroxyapatite structure with citrate as a complexing agent. And these are the different questions that we tried to answer. Yes. So first of all, I would like to show you this. This is what we have experimentally. So these are our spectra. This is our control, meaning the clean one, the clean apatite. Then we have it with acetate. The dotted one, and the dashed one we have here with citrate. So the question is that with these spectra, how can we get some information, geometrical information on the interaction of citrate with the surface? So this is more or less what we want to obtain. Yeah, pH 7. Okay, so it's still biological. Yes, I think I will not read the questions. You can see them. Yeah, the models again. We started with 3 orientations, 3 surfaces. We put water on it, equilibrate it. We put the water on it, and then we put in the water. We put 3 orientations of our citrate. Yes, so we call it P1, V1, P2. I say that because you will see that in the structures later on. Yeah, so this is typically the systems we calculate. It's all DFT here. CP2K was used for the calculation. So no force fields. Some technical details for those who are interested. So all again, PBE functional corrections for dispersion, a CP2K quick step package, and then the base sets. So the idea is that with our molecular dynamics, we can calculate, in fact, mainly what happens is that we extract the change in dipole moment in order to, at every step, in order to obtain this kind of spectra. Yeah, good. And we will compare it with and without citrate. So the water interface, water apatite with the citrate that you see here. Okay. Again, this is how we calculated that. We model, in fact, we introduced three orientations: this V1, V2, and P1. Why? Because it lasted too long to wait for the orientations to have them, let's say, equilibrated. This is the same as in the beginning of the talk, that when we want to accelerate. So we know that it will be dynamic, but we need to fasten up the accelerate the calculation. And so we started with 3, let's say, intuitive structures. Yes, and so we are sure, we are not sure, we're never sure, but we as sure as we can to not forget any critical orientation of our complexing agent. Yes, we did our molecular dynamics calculation again in NVT example for, and then we calculate the radial distribution function. Then we moved to NVE, and with this data we extracted our dipole moment in order to obtain a spectrum. Yes, infrared spectrum. These are the data. So we compare it with the experiments, and we will compare the experiment. What you see here is our crude data, and for the different situations, without citrate and with citrate, the 3 orientations. Okay. So now what is important, what we see is what happens in this region. Okay. This is in fact the water bending region. Yeah. I go fast. If you take a look at it, you will see it is important. So if we enlarge this, we see this thing. Yeah. You see there is nothing here. Yeah. This in the pure water is nothing. So the fact when you have this appearing, this means there is citrate. Okay. So now the question is, if we go have a look in the experimental data, which one will fit the best? Which model will fit best to the experimental spectrum? Okay. And in fact, we see 2 bands appearing, and then we can see this, and it is about the 1570 and the 4060 3085 region. And in fact, we recover this data, but the question is now, what is it? From where does it come from? Yeah, and in fact, what we've seen is that thanks to the radial distribution function, so we see the distances, and we see the interaction between the cation, the calcium, and our anionic group. We can in fact isolate the different vibrations. We call that a vibrational density of states. Okay, and so for the different families, we can in fact, you see, isolate the vibrations which are only attributed to water, to the citrate here in the purple one, and the solid, so our hydroxyapatite in blue. You see, and what we see here is that for the 3 orientations, we can in fact pin very precisely which band corresponds to which vibration. Okay, so this is quite powerful, and if we do this, we analyze that, then we can in fact say that, yeah, look, our bands here, the 1570 is associated to the citrate C carboxylic group, adsorbent hydroxyapatite, and the 3050 is arising from the OH band. You see that there is an OH band here in the hydroxyl group. Yeah, so we adsorb it like this. This is finally the final geometry that we obtained. I think I will finish with that. I think I'm in time, I hope. So I would like to finish, not directly, but first I would like to acknowledge all the people that were involved in these studies during the different years on which I am working on that. So we have, the last studies were done by Flavio Cirobigiano, who is now in Paris in Sorbonne University. He left a few weeks ago. We have the PhD, which is postdoc, is Dr. Brigiano. And then we have Yang Su, who is PhD student, who will finish very soon. Yuan Zhao, who is a master student, and Anjali also, who is a master student. So they worked on they produced the results. Then we have our experimental partners that are very thankful in order to compare and explain our results. So we have people in France, at the university, but also at the hospitals. We work a lot with hospitals, and we have also some people from South America. This is the finance. Yeah, without that, no calculations. And then I would like to thank you for your attention. Thank you very much.